guys, this is 10.2, the second part. So here's the other example. It says, how quickly do synthetic fibers such as polyester decay in landfills? A researcher buried polyester strips in the soil for different lengths of time, then dug up the strips and measured the force required to break them. Breaking strength is easy to measure and is a good indicator of decay. Lower strength means the fabric has decayed. If I start looking at the data, there's two groups here, one after 2 weeks and one after 16 weeks. So we would expect these, okay, in general to be lower, okay, because they've been buried longer. They have lower strength. All right. So it says for one part of the study, the researcher buried 10 strips of polyester fabric in well-drained soil in the summer. The strips were randomly assigned to two groups. 5 of them were buried for 2 weeks and the other 5 were buried for 16 weeks. Here are the breaking strengths in pounds. So in one of these, it required 118 pounds of force to break that for one of the strips that had been buried for 2 weeks. Do the data give convincing evidence that polyester decays more in 16 weeks than in 2 weeks? So it doesn't tell us an alpha level. Okay, so we have to assume an alpha level. This isn't a medical problem, so I'm going to stick with an alpha of 0.05. And let's go through our process once again. Okay, so step 1, statement. And the statement are going to be my hypotheses. So my HO and my HA, my HO and my HA. All right, so it says, the data give convincing evidence that polyester decays more in 16 weeks than in 2 weeks. If that's true, we would expect group 1, okay, all right, more decays more means less strength to break. All right, group 1 was the one for less time. So we think that's going to be more. It's going to require more force to break, meaning that it's decayed less. So my alternative hypothesis is that mu1 is greater than mu2, based on the way they term the groups, group 1 and group 2. That would make the null hypothesis that mu1 is equal to mu2. All right. Again, define your variables. Tell the reader what these represent. All right. So where mu1 is the true mean breaking strength required to break polyester fibers after being buried for 2 weeks. And mu2, okay, it's the true mean breaking strength required to break polyester fibers after being buried for 16 weeks. So it's defining what those parameters are. And remember, we can rewrite that as mu1 minus mu2 equaling 0. We can rewrite this one, mu1 minus mu2 would be greater than 0. So that's our statement. All right. Now this is an experiment. So with an experiment, we do not have to check the independence condition. All right. So step 2, we're going to do our conditions, check. All right, random. There's no random selection here of the fibers. Okay, but there is random assignment. So I would say random assignment to the groups stated in the problem. All right, independence. Remember, we do not have to check this one. All right. Now I can just say not required in an experiment. But I do have to make sure we have normal here. So, don't know anything about the shapes of the population distributions. My sample sizes for each of the two groups is only 5. So, I might say something like this: population shapes not known. Okay, CLT does not apply. All right, so what we should do is we should check the data for any strong skewness or outliers. So if I go into my list here, let's go ahead and delete list 1 and list 2. Make it a little bit less dark. So in group 1, the strengths are 118 pounds, 126 pounds, 126, 120, and 129. And for the next group, breaking strength required is 124 pounds, 98 pounds, 110, 140, and 110. So if I want to plot these, let's look at group 1 first, which is an L1. And then we can do a zoom 9. Okay. Data's kind of condensed. The whiskers aren't too long. I don't see any outliers, which is good. All right. So I can copy this box plot, something that looks like the box plot, onto my paper. It kind of looks like that. And I can give the values here. We can say group 1 sample data. All right. So the min is 118, Q1 is 119, median is 126, Q3 is 127.5, and the max is 129. We can do the same thing for the second group. So I can go back under my stat plot. I can change the data to list 2. And then do my zoom 9 and look at that data. All right. Again, I don't see any outliers, no strong, really strong skewness. So that's probably okay too. It looks like that. And the median's about right there. Group 2 sample data. Okay. The min is 98. Q1 is 104. The median's 110. Q3 is 132. And the max is 140. And I would write something to this effect. I would say that sample data for both groups show no outliers nor strong skewness. Okay. Since T procedures are robust, we will assume that the sampling distribution of x bar 1 minus x bar 2 is approximately normal. So now we're done with the conditions check. Okay. We're good enough on that. Now we can go to our calculations phase. All right. The data comes from two separate samples. So this is a two sample, and it's a test, and we're going to be using t-procedures. So it's a t-test. All right. And we're going to be assuming an alpha of 0.05. All right, so our test statistic is going to be t. So t is going to equal the sample difference minus the hypothesized parameter. So we're assuming that there is no difference, all over the standard error of the sampling distribution of x bar 1 minus x bar 2, which is s1 squared over n1 plus s2 squared over n2. Okay. And then I can give the values of all these statistics. So x bar 1, x bar 2, I would say S1, S2, N1, N2. I know those are going to be 5 because there's 5 sample points. Okay. And whatever the calculator tells me the degrees of freedom are. Okay. Now I put the data into the list, so let's just use our calculator to help us out. We go stat, test, and we're going to look for two t-tests. Okay. Data comes from two samples, two unique samples. We're using the t for our test statistic, and it's hypothesis test, so that's why we choose that option. Okay. We have actual data. So if they only gave me stats, I would use stats. Okay. But I have actual data. So list 1 is an L1, L2, all right? And then to figure out what we're talking about here, we think that mu1 is greater than mu2. So that's our test. It's mu1 is greater than mu2. It's going to be a right tail test. We choose pooled no. We hit calculate. It's going to give us everything. So x bar 1, 123.8. Okay. So that was the 2 week. It took 123.8 pounds on average. Okay. X bar 2 is 116.4. These would all be pounds. Okay. S1 is 4.604. S2 16.087. All right. Degrees of freedom 4.65096. Okay. Come back up here. That's our test statistic t. So the t here equals the 0.98887 if I round. That's the p-value. P-value is 0.1857. So that's what we're really looking for, these two values in our calculation. Okay. Now, I mean, it looks like there's a difference. That looks like a significant difference. Why do you think the t-value is so low and our p-value is so high? Well, sample size is a big reason. If you only have 5, all right, think about it. If these are only 5, then this quantity is going to be bigger than if n was larger. Okay, well, if your denominator is bigger, your whole t is going to be smaller. Okay, so when you only use a minimal sample size, all right, that's going to majorly affect how close t is to the center. All right, so in my picture here, if I make my t-curve, all right, we're expecting 0 down the center of the sampling distribution, because that's the hypothesized parameter, and we're getting a t-value not quite equal to 1 standard deviation above the mean. So that's 0.989 essentially. We look at our alternative, which is a greater than. So the area to the right of there is this, about 18%. So what's the p-value mean here? If there really was no difference between the mean breaking strength required, all right, then we would expect to get a sample difference. Okay, we would expect this difference right here, which is about 7.4 pounds. We would expect to get a difference of 7.4 pounds 18.57% of the time, which isn't likely, but it's still very plausible that we would observe something that extreme, a difference of 7.4 pounds or more, 18% of the time. Okay. Right. Now we do our decision. And here, the alpha is this. P-value, this is way bigger than that. So my decision, okay, p-value is greater than alpha. You need to write that, whether it's greater or less, you need to make that statement. Okay, so you're showing linkage. If p is low, reject the O, but the p is not low here, so we fail to reject HO. So that's the decision. The last step, I need to conclude. All right. Since I failed to reject, I start my sentence with, there is insufficient statistical evidence at the alpha equals 0.05 level to conclude that polyester fibers, put it back in the context of the question. They're asking me, do polyester fibers decay more in 16 weeks than in 2 weeks? We don't have enough evidence to say that. But polyester fibers decay more in 16 weeks than in 2 weeks. And that's that problem. The calculator only gives you this step of the process. So if you only do this and you don't do the rest, you're not going to get very many points. Because while you got the correct values for the calculations, it's your interpretation of that that's important. All right, really, that's important, that's important, that's important, and that's important. Everything's important here. Right? The numbers give us a way to conclude. So, all right, let's just go on to the last page here. This is an important one. All right. Excuse me. It says when the inference involves the difference between two distinct or different groups, okay, we use the two sample procedures. Okay, we would either use two samp, all right, so two sample t interval, all right, two samp t test, that's the case for means, and then proportions we would use two prop z interval or a two prop z test. All right, when we have two distinct groups, we would use one of these four. Okay. Now, if the inference involves the difference, such as a before and after, a right and left, or some sort of matched pairs design for just one group of subjects, okay, we would take the individual difference for each subject, and that's called paired T procedures, and use one sample procedures. Okay, be very careful that you are using the right test, it should say correct test, or interval, based on the situation and context of the problem. The proper method of analysis Depends on the design of the study. All right. So it says in each of the following settings, decide whether you should use paired T procedures or two sample T procedures. So this applies to means. Okay. Applies to means problems. To perform inference and explain your choice. All right, so part A says, to test the wear characteristics of two tire brands, A and B, one brand A tire is mounted on one side of each car in the rear, while a brand B tire is mounted on the other side. Which side gets better which side gets which brand is determined by flipping a coin. Okay, so there's some sort of random assignment there. Okay, so what we're going to do is each car might be different. We're going to look at each car individually and compare A and B. So you're matching up some A and B in each case. All right, that's what it's like. You're matching an A and B on each car. All right, so there's some sort of matched thing going on here. So since this is some sort of matched pair, we would use paired T procedures. Okay. Because although there's two distinct different brands, you're looking at it for each car. So each car is its own grouping. All right, each car is its own grouping. So we would use paired T procedures. All right, so let me kind of illustrate this. Like, so in part A, let's say I just had like 10 samples. All right, so brand A tire, brand B tire. And maybe we would look at it for like 10 different cars. Car 1, car 2, car 3, ... all the way out to car 10. All right, and maybe in this one, so maybe the wear on brand A is 14, whatever units they use, and this one's 8, and maybe this one is 12, and that's 9, and this one might be 10, and that one might be 11, ... This one might be 13, and that one might be 7. What we would actually do is we would take the difference for each car. So 14 minus 8 is 6, 12 minus 9 is 3, 10 minus 11 is -1, so on and so forth. 13 minus 7 is 6. And then we would actually just use this data to get a mean difference. Okay, so we treat it as one sample. Right? So if you're going through this, it's just, if you were doing a confidence interval, you would take X bar D, that's your sample difference, plus or minus a T star based on degrees of freedom for a single sample. So that would be based on degrees of freedom of n minus 1. In this case, if I have 10 cars, I would just use 9. There's not some complicated thing you have to do for degrees of freedom there, because you have 10 different cars that you're mounting these tires on. All right, times the standard error, which would be the standard deviation of the difference over the square root of n. So it works exactly like a one sample t interval. Works just like a one sample t interval. Right? And then if it was a hypothesis test, you might assume that there is no true difference. All right, and maybe your alternative hypothesis is that there is some sort of difference between the wear of the tire brands. And in that case, your t statistic would be the sample statistic minus the hypothesized parameter over the standard deviation of the difference divided by the square root of n. All right, so it's treated just like a single sample. Paired t procedures just like a one sample. All right, now let's read part B. It says, can listening to music while working increase productivity? 20 factory workers agree to take part in a study to investigate this question. Researchers randomly assign 10 workers to do a repetitive task while listening to music, and another 10 workers to do the task in silence. Well, these are distinct groups. You're not matching one person up here, okay, in the first group to another person in the next group. All right, because these are individual or distinct groups, and they're not matched in any way, we would use two sample procedures. And we would want to be looking at the difference in the individual sample means. Okay, just like we've been doing in the rest of this. So these can get a little confusing. Just ask yourself, are these matched up in some way? Or are they paired in some way? Or is it the same person, like a before and after situation? In that case, you would use paired procedures and treat it like a single sample, right, and be looking at the differences of before and after. But in this case, if they're two distinct groups, all right, that don't have a connection to one another, you'd be using two sample procedures. All right, and that's gonna end it for chapter 10 here. There's only two sections, so stop it there.